Yeah, I'm Alvaro Sarasua from the NTG Universitat Pompeu Fabra in Barcelona. I co-authored this work with Baptiste, Caramiaux, and Atau Tanaka from Gaussian Mixture University. And in this work, we deal with expressive gesture-based interaction. So we deal with how to extract expressive characteristics from motion, which has a number of problems, including one which we deal with in this particular work, which is the fact that sometimes these expressive variations are idiosyncratic. So you have personal elements that you have to take into consideration when trying to extract the expressiveness from gesture. A good example of this is music conducting, where you have conductors developing their own personal style to express particular things in the music, even though conducting is a highly codified and taught task. So if you build an interactive installation of conducting, you might want to include this idea of developing your own style for expressing a particular thing in your installation. Here in particular, we deal with music articulation, so the ability to express how the notes should be played, so whether it's legato, being long connected notes, or staccato, sharp notes. We will see this later in more detail. And we use for this a human-centered machine learning approach, where we allow the user to tell the system how to interpret his gesture and to extract articulation from that. So I'm going to explain how it works together with the user study that we undertook to evaluate it. The idea is that first, the user tells the system by giving examples of the gesture variations how he understands that these articulations are expressed. So in this case, we, in the study, presented the user with 3 variations, the same melody being played with 3 different syntheses, basically controlling the envelope of the notes. So for legato, it would be like long notes with long attack, long release, and for staccato, short attack, short release. In the study, we asked users to give 3 examples ranging from completely legato to completely staccato, being normal, what we call something in between. And then afterwards, during performance, once the model has learned your interpretation of articulation, it is able to analyze in real time where you fall in this space and provide an inferred articulation that controls the sound engine. And also for the study, we included a slider where users had their task. So, for example, you have to do completely legato and the inferred articulation in real time. We had 10 musicians and 10 non-musicians to test whether the musical expertise affected how this was working. In the following videos you're going to see, take into consideration that what you're going to see is also what the users were seeing. So they have a screen in front of them where they can see themselves, a trace of the gesture, and the slider on top right. So first, for the training, I'm going to show how the user provides examples, and these are represented in the future space, basically computing velocity and acceleration from the gesture. Please remind that the sound synthesis was done to make it very clear the distinction, not to make it musically interesting. So the idea is that before doing this, the user was already presented with these 3 variations, and then he thought, okay, I'm going to do it as I want. They can rehearse as much as they want and so on, and then they train the system accordingly. So these 3 variations are represented in the future space, and what you expect is to have this sort of distribution where you can tell the different classes. So you build then a probabilistic model with which you can perform classification and to tell whether he was doing a legato articulation, normal, or staccato articulation. So then, during performance, the user is presented with one of the examples, so legato, normal, or staccato, and then he has to control for a certain time the system reaching the goal articulation, so to say. So we analyze the last time window of the movement, compute the same descriptors, and see where this falls in the feature space. the interesting thing is that we are not doing classical classification, so to say. We're doing soft classification, so the idea is that the output you get is a continuous number ranging from 1 being, for example, legato, to 3 being completely staccato. So you can move all around the space. Now the user is going to control the system, trying to be in the middle. I particularly selected one that is not perfect, but also because it gives a better idea on how he's trying to get to the goal. So you see that the sound synthesis changes as he controls the articulation, and the idea is that in this task he has to take it to the middle. There are better examples where it's completely fixed, but this is a better illustration on how it works and how they explore this space of articulation. So in order to analyze what happened, we computed the accuracy by taking the difference from the black line, which would be the articulation that he was getting during the time, to the target, which in the case I just showed would be the yellow line being the normal target. And the same for all the trials that we had. The average accuracy, averaging across all participants, was 0.31. And also, interestingly, it was correlated with their self-reported sense of control. So after the task, they were asked, did you feel that you had control over the articulation? Do you think you fulfilled the task? And the accuracy we got for each participant and their answer to this question, which in average was of 5.3 over 7, was correlated by 0.6. Interestingly, the accuracy was better for musicians than for non-musicians. So in order to understand how this went, we've made further analysis looking at whether the quality of the training, so how they had trained the model, had an influence on the performance. So the quality we measured by taking the separability of the classes. The image on the left would correspond to a bad training, so to say, because it's hard to separate classes. The image on the right would correspond to a good training because it's easy to separate classes. We found that the training quality was not linked to expertise, so both musicians and non-musicians were able to create easily separable classes, and also it was not linked to the accuracy during performance, so there's something else going on. We further made some exploration on the data from the training, finding that the error doing cross-subject validation was very high, which indicates that actually the articulations we were learning are indeed idiosyncratic, so personal for each of the subjects. And we computed the within-subject cross-validation, trying to compare it with the accuracy we got during performance. Interestingly, it was better, the accuracy during the performance, than training and testing with the training data. So this gives an idea of how the reinforcement effect that getting the output in real time gives to the user, allowing for better control. This related to the fact that all non-musicians except for one stated that they were not paying any attention at all to the audio in the questionnaire, indicates also that that may be another reason for the musicians performing better than non-musicians. So to conclude, the model provides control using idiosyncratic variations, as we saw in the cross-subject comparison. Musicians perform better than non-musicians, but not because they are able to train a better model, so a more separable model. And mainly it's because the audiovisual feedback of the Gaussian mixture model in real time reinforces the user on his actions. For future work, we are now working on extending the model to control the other expressive characteristics of sound, so of music, so mainly tempo and dynamics, which may need to include a temporal model of gesture. So that's it. I'll be happy to take your questions. So.
I have a quick one. Have you considered looking at more diverse gestures and also maybe varying times of those gestures?
Yeah. So the idea is ideally, the output would be that, so the ideal interaction would be that you can do different gestures. So, for example, 4/4 and 3/4 instead of just figure 8, and also that you can vary tempo and dynamics. For this, using velocity and acceleration imposes a kind of a limitation, because if you change tempo, it will fail. So, including a temporal model of gesture can help to do this, either by taking a decision based on what the tempo is, or on using the gesture variation that you extract to train the model instead of using directly the features you extract from motion.
Yes. Let's thank Alvaro again. Thank you.